I need to talk about control hazards. Okay, control hazards. So what are control hazards? Now, these are caused by control instructions. What are the control instructions? They are mentioned here, jump and branch are the control instructions. Now, why do they call them control?
They change the PC.
Exactly, they control in what order we execute the instructions in the program, right? They change the PC. We use them to implement loops, if statements, and so on. We already have seen these instructions, right? In the assembly language. So when we write the code, these are the control instructions because they can control in what order we execute. So we can jump, we can branch, and therefore we can use them to implement some the if statements and the loops. These are called control structures that we have in programming, and therefore they can control in what order we execute the instructions. Right. Let us focus on these. Now, we did not really have a problem with these when we dealt with a single cycle or even the multi-cycle. It's not really a problem when we have serial execution. But because of pipelining, there is a problem that I would like to mention about these instructions specifically, about the jump and the branch. Okay, so in the case of the jump, it's easy. All what we care about is the jump target address. That's all what we need in the case of a jump. We don't need anything else, right? Because the jump is always taken. You say jump to this address, all what we need is the jump target address. That's it. In the case of a branch, we need two things. We need the branch result. So in the case of a branch, we have to execute the branch. Now, why do we execute the branch? Because I need to know if the branch is taken or not taken, because the branch has a result. The result here is the outcome of the branch, which says that taken or not taken. Now, if the branch is taken, we have to branch into the branch target address. Okay, that's if the branch is taken. So we need the branch target address. So we need two things in the case of the branch. We need the branch result, taken or not taken. And also I need the target address. I need to know where to branch in memory. That's the target address. If the branch is not taken, then we simply increment the PC. PC becomes PC plus 4. That's it. We go to the next instruction in memory. That's if the branch is not taken. On the other hand, is taken. This is why it's called conditional, okay, branch. Okay, so in the case if it is taken, then what we have to do is that we add to PC plus 4, we add 4 multiplied by the immediate. So there's a 16-bit immediate inside the branch. And this immediate is signed. It can be positive or negative. Positive means we have a forward branch. Negative, it means that we have a backward branch, right? And therefore, it means that we have, this is in the case of loops, we branch backwards. Right, so that's the branch target address. Okay, so the branch target address can be computed early in the pipeline, but we need to execute the branch. We need to know the outcome of the branch. So if the branch is taken, we have to go to the branch target address. If the branch is not taken, we just go to the next instruction in memory. PC becomes PC plus 4. Right, so in the case of jumps and branches, first we have to fetch them. Okay, so we fetch them from the instruction memory. So once we have, the instruction will be in the second stage of the pipeline. So during the second stage of the pipeline, we examine the opcode. This is when we decode the instruction. So we decode the instruction in the second stage of the pipeline. We examine the opcode. Then at this point, we can tell if the instruction was a jump or a branch. So we know from the opcode what is the instruction. But at this point, once we have the instruction in the second stage, already we are fetching an instruction in the first stage of the pipeline. Now, that's the problem. Okay, so for this reason, we say that the jump has a delay. Because of pipelining, okay, the jump instruction has a delay which is equal to 1 cycle. Now, this delay is created because we are decoding the instruction in the second stage of the pipeline, because we have to fetch it first, and then in the next cycle, in the second stage, we decode the instruction and we know that it is a jump. So by the time we have updated the PC, already we have fetched the next instruction from the instruction memory. So that's the 1 cycle delay. In the case of a branch, it is even worse. Okay, it is a 2 cycle delay. Why it's a 2 cycle delay? Because first we have to, okay, after fetching it, we decode it in the second stage, but also we have to read from the register file, and then we have to execute. And then when we execute the instruction in the third stage of the pipeline, so we have to use the ALU to determine the outcome of the branch, whether it's taken or not taken. So we have to do a subtraction. Okay, in the case of a branch, if equal or branch not equal, we subtract, right? Now we do a subtraction to detect if they are equal or not. So we need to know the outcome of the branch result, taken or not taken. So by the time we have executed, not only we have the next, but we have 2 instructions in the pipeline that come after the branch. 2 instructions are in the pipeline. Now, if the branch is taken, these instructions are not really supposed to be in the pipeline. So we have to remove them from the pipeline. So that's the problem with the branch instructions. So people have faced this problem, okay, since the early days. Okay, when people have implemented pipelines, this goes back to the 1980s, and they face the problem of the jump and the branch, specifically the branch, because the branch is actually, we have to execute it, and we have to determine its outcome. Let us take a look at the jump first. So here's an example. I would like to say jump L1. L1 here is my label. L1, this is actually my target instruction. Now, this is my next instruction that comes in memory. So during clock cycle number 1, you fetch the jump instruction. We don't know it is a jump because we did not really fetch it yet. So first you have to fetch it from the instruction memory. So this is the instruction fetch stage. What is shown here is the instruction memory, really. And then during the second cycle, this is during clock cycle number 2, we decode the instruction. So this is my instruction decode stage. Okay. So at this point, the instruction decode is going to examine the opcode, and there is a unique opcode for the jump instruction. So at this point, we know that it is a jump, and we are going to update the program counter with the jump target address. So we can calculate the jump target address, and then we can update the PC, and then the jump will take place. I have a comment here. Right. So let us continue. Khalid, are you able to join? There was a comment that can you all hear me? Is it clear?
We hear.
Yes.
Okay. Okay. Good. Right. So so notice that again the problem with the jump. The problem with the jump is that by the time we have decoded, okay, the instruction during the second stage of the pipeline, what happens is that the next instruction is being fetched, right? So notice that here, the next instruction, it can be any instruction. Okay, it can be an ALU instruction, or it could be something else. It does not really matter. It could be a load, it could be whatever. Okay, so this instruction is being fetched. And this instruction is being decoded. The jump is being decoded. Now, by the end of clock cycle number 2, the jump is going to update the PC. This is actually my PC register here. Okay, it will contain the address of the target instruction so that we can start fetching at the target instruction. What shall we do? What shall we do? Can we allow the next instruction to proceed into the pipeline? Can we allow this? Can we allow the next instruction to proceed?
No.
Okay,
because we have jumped.
Exactly, because we are jumping. So therefore, this instruction, next instruction, is not really supposed to be in the pipeline. So what we have to do is that we have to convert this instruction into a bubble. That can be easy. We can clear all the control signals, or we can convert the next instruction into a no-op. Okay. A no-op is an instruction that does nothing. And it basically, it will, whatever computation it does on the, it could be, for example, it can do anything on the ALU, as long as it does not rewrite any register in the register file, as long as it does not write anything into the in the data memory, in the memory stage. so it does not restore anything in memory, then in this case, this instruction has no effect on the pipeline. So it will be in the pipeline, but it has no effect. So we call it a bubble. That's the meaning of bubble. So we can always convert the next instruction into a bubble, and therefore there is no harm, which is done. Now we waste one clock cycle, so it's going to impact the performance, but it does not impact the correctness. So the pipeline is correct. The next instruction does not really have any impact because we have converted into a bubble, but the pipeline, so we are going to lose one cycle. That's it. Okay. Now that's in the case of a jump. In the case of a branch, it is worse. Why? Let us take a look at this. So here I have a branch instruction. It says branch if equal T1, T2, and L1. Now the branch is conditional. Unlike the jump is unconditional. Okay, but the branch is conditional. So we have to read two registers, and then we have to compare. We compare by doing subtraction. So we have to execute the branch on the ALU, and then we decide whether to branch or not to branch. Okay, so in this example, first we fetch the branch instruction during clock cycle number 1. That's basically my instruction fetch stage. This is basically my instruction memory. Fetching it in the second clock cycle, we have to read T1 and T2 from the register file. So this is my instruction decode stage. Okay, so this is during clock cycle number 2. So we are decoding the instruction. The branch if equal has a unique opcode. We know we can tell this from the opcode, right? So the opcode is unique. So we notice that, okay, so the control logic is going to decode the branch if equal, is going to notice that it's a branch. And at the same time, we read T1 and T2. Now, after reading T1 and T2, we want to execute. We would like to check if the branch is taken or not taken. So that will be done in the third stage of the pipeline. So here the ALU during clock cycle number 3 is going to execute the branch, is going to do a subtraction. And then if the branch is taken, suppose that they are equal, then the branch will be taken. So we are going to branch and change the PC into the branch target address. Now notice that I have next 1 and next 2. I have 2 instructions in the pipeline that come after the branch instruction. So next 1 has been fetched during clock cycle number 2, and next 2 has been fetched while we are executing the branch instruction during clock cycle number 3. So the problem is that the delay of the branch is 2 cycles because we are executing it in clock cycle number 3, at which point we have fetched 2 instructions that come immediately after this branch. So the branch here, so these 2 instructions are not really supposed to be in the pipeline because we are supposed to skip next 1 and next 2 and move directly to the target instruction here at L1. That's what we are supposed to do, right? This is what the pipeline is supposed to do. Okay, so but next 1 and next 2 are in the pipeline. So how do we fix this problem? So this is the meaning of the hazard. This is the meaning of the hazard. If we allow next 1 and next 2 to be in the pipeline, then these might update some registers that might store into memory. So therefore, this will create a problem. What shall we do?
We insert stalls.
We convert them into bubbles. We convert them into bubbles. So all what we have to do, convert them into bubbles, next 1 and next 2. Okay, and therefore the pipeline will work correctly. Okay, it's going to work as it is supposed to do. Okay, producing correct results. Is going to eliminate next 1 and next 2 from the pipeline. Now this is if the branch is taken. Okay, this is if the branch is taken, and therefore we update the PC and we start at the branch target address. Okay, so we go to the target instruction at L1. Okay, is this clear?
Yes.
Right. Let us continue.
Doctor, unlike the load word, we don't really have to freeze the PC. There is no need.
No, well, in this case, we don't exactly. We have to deal with it differently. Exactly. So unlike the load word, in which actually the instruction that comes after the load is going to wait in the decode stage and we freeze the PC. No, here we don't freeze the PC. So therefore, this requires a different solution. So therefore, we need to fix the pipeline in a different way, specifically to deal with the jump and the branches. So we allow the instructions to be fetched, but we convert them into bubbles. That's a different way to handle, okay, the branch and the jump instructions. So remember, in the case of the jump, the delay is just 1 cycle. In the case of the branch, it is 2. So we need to get rid of the next one and next 2. Right, let me ask you this question. What if the branch is not taken?
It will go to the next one and next. Actually, I always have a question.
Should we convert them into bubbles?
No.
No.
Okay, so this is basically conditional, right? That's conditional. So if the branch is not taken, there is no harm of having next one and next 2. Already we have fetched them. So by the time we have determined the outcome of the branch, so here the ALU during clock cycle number 3, by the end of clock cycle number 3, we know if the branch is taken or not taken. At the pipeline will know, okay? So the CPU will know that if the branch is taken or not taken. So if the branch is not taken, already we have next one and next 2 in the pipeline. Why should we convert them into bubbles? We only need to convert them into bubbles if the branch is taken. But if the branch is not taken, then we allow them to complete normally. We do not branch and we continue normally. This is actually shown here. Okay, so we call it a predict branch not taken. In other words, if the branch outcome is not taken, okay, if the branch outcome is not taken, next one and next 2 have already been fetched. So by the end of clock cycle number 3, we know this. Okay, already we have computed, okay, the outcome of the branch. Okay, and we know that the branch is not taken. At that point in time, we should not convert next one and next 2 into bubbles. So we allow them to proceed and we continue normal execution. Okay, and therefore we do not really waste any clock cycles because we did not really convert them into bubbles. We simply do nothing, just allow the program to continue. Ali?
Yes. What if the branch outcome will be taken and the next one will be jump? It will be fetch and because jump.
Yeah, well, in this case, the next one, if it is a jump, it will have no effect. And therefore we do, okay, that's a good question, by the way, Ali. That's a good question. Right, let us take a look actually, okay, let me address how we implement the jump and the branch, and I will address your question, okay? But you have actually an excellent question. So what if I have a branch which is followed by a jump, right? And the branch is taken. This is the question, right?
Yes.
Okay, I just would like to make sure that all your colleagues understand. Okay, so do you understand this question, students? So Ali is, yeah, so he's actually raising a very important question, which is, what if I have a branch, if the branch is taken and this is followed by a jump? Should I branch or should I jump? What do you think? Well, we should branch because the branch actually comes first in the program, right? I should not really jump. So we have to ensure in this specific case, of course, these next one and next 2 should be converted into bubbles. But if it's supposed that they were not ALU, they were actually like jump or branch instructions, we ensure that the branch, if equal, will be taken and we branch, and the next one will not jump, okay? Because that actually will cause a problem, right? Right, let us take a look at the implementation and see if it works, okay? If we need to handle this case specifically. Let us now implement the jump and the branch in the pipeline. So now we go into the details. We understand the problem. We understand the hazard. This is why I call it a control hazard. Okay. Now this hazard is caused specifically by pipelining. Remember, in the case of serial execution, we complete the instruction before we start fetching the next one. So there was no hazard in the case of serial execution. But because of pipelining itself is creating the hazard. Right. So now we focus on how to implement, okay, the jump and the branch in the pipeline. Now notice that here we have the PC control. That's the PC control here. This is going to control this multiplexer. This is very important. Let us understand this. Now, once we have fetched the instruction, notice that we have this instruction register. Once we have fetched the instruction, we have the opcode. What's important to me in the case of the jump and the branch, I need to examine the opcode. So this opcode is going to be decoded by the main control here. And we have the jump here. This is a control signal. So if the opcode is equal to the opcode of the jump, I think it's equal to 2 or 3. I forgot. I think jump is 2, jump and link is equal to 3. We have this jump control signal. Okay, it means that we have to jump. So this jump control signal is sent to the PC control, as we have done in the case of the single cycle. The same thing in the case of pipelining. The same. So we have to jump. Now, here is the trick. I'm going to introduce a multiplexer here. Now, this multiplexer is going to inject a no-op into the instruction register. So I did a modification. I introduced a multiplexer. Okay. Now, this multiplexer, if you are jumping, I call it the kill signal, kill 1. It means that kill the next instruction. So the instruction that appears here at the output of the instruction memory, we are not going to actually to feed it into this instruction register. I'm going to force a no-op. Now, a no-op, okay, will be an instruction which is encoded as zeros. So basically, the way that we encode the instruction, so basically we introduce a 0 instruction. All the 32 bits of the instruction are all zeros. So basically we introduce a 0 inside this instruction register. Now 0, it means an R, because the opcode equal to 0, it means R type. And RS, RT, and RD are equal to 0. So basically we are reading and writing basically register 0. Writing register 0 has no effect. So basically the instruction is going to be allowed to proceed into the pipeline, but it will have no effect. So that's a bubble. Okay, that's my bubble. Now that's if I have a jump instruction. So the jump here, okay, once we have detected that we have a jump, okay, then in this case we kill. Okay, that's the meaning of the kill instruction. We replace the instruction, the next instruction which is being fetched, that appears immediately after the jump, we replace it with a bubble. So therefore, the bubble will be propagated inside the pipeline. So that will solve the problem of the jump. Right? How about the branch? Okay. In the case of a branch, I might actually have branch if equal or branch not equal. So these are the two branch. Okay, so I'm dealing with only these two instructions. I might also have other branches. So this is actually is my branches based on the opcode. Notice that here we can wait until the execute stage. So these are my control signals. Okay, and these control signals will be propagated into the execute stage in the case of a branch. So we have a branch if equal or branch not equal. So we wait until the third stage of the pipeline. We wait until the third stage. So if I have a branch if equal or branch not equal, okay, we need the outcome of the ALU. We need the 0 flag. So notice that here I have the 0 flag because I need the 0 flag to determine if the branch is taken or not taken. So the PC control is going to determine if the branch is taken or not taken. If the branch is not taken, there is no need to do anything. Unless it's not taken, allow the next two instructions to proceed into the pipeline. Now notice that I have, okay, my first instruction here is, so I have an instruction which is being fetched from the instruction memory, but also I have a second instruction which is in the decode stage. So by the time we have the branch in the third stage of the pipeline, I have next one is in the second stage and next two is being fetched. Okay, so we have two instructions that we need to kill. So in addition to kill one, I need to have kill two. So notice that if the branch is taken, I have an instruction which is here available at the output of the instruction memory. But I also have a second instruction which is inside this instruction register, which is being decoded. It has its control signals. So the kill one is going to convert two instructions into bubbles. The one which is being here fetched is going to be converted into bubble, but there is also a second kill here, which means that we introduce another bubble, okay, another bubble into the execute stage. So two bubbles, not just one in the case of a branch when the branch is taken. Okay, right. Let us take a look at the details of this PC control. Now that's actually is, okay, the question that will address the concern of Ali. So here I have the jump control signal. These are actually my branch control signals. Notice that either we have branch if equal and we have the zero flag. The zero flag equal to 1 means they are equal, okay? Or we have branch not equal and they are not equal. So either this or this. In this case, we say that we are branching. Right. Why do I need this AND gate? Okay, notice that here it says that if you are jumping and not branching. So we have here the outcome. Notice that here we have the outcome here of this PC control is this PC source. 0, 0 means that we are not jumping, we are not branching. 1 here means that we are jumping, and 2 means that we are branching. Okay. So now, if we are branching, if this branch here is equal to 1, and we are not jumping, then in this case, we say, sorry, let me say it again. If this is a branch, khalas, we branch. We say it's actually here 1. Now, jump will be equal to 1 if it is a jump and it's not a branch. Now, this will handle the situation in which we have a branch followed by a jump, according to the comment of Ali. If we have a, so notice that here jump, I have a jump here signal that indicates that we have a jump and not the branch. What does it mean? It means that you might have here, okay, a branch instruction in the third stage, followed by a jump and also a jump. So this might be true and this might be true at the same time. Okay, Ali? So the jump is equal to 1 and the branch will be equal to 1, one of them. Yeah, it could be branch if equal or branch not equal. So we are branching and we are jumping. So the instruction which is in the third stage of the pipeline is a branch instruction, while the next instruction, which is in the second stage of the pipeline, is a jump. So according to this control logic, it is a jump. So we have a branch and also we have a jump. But if the branch is taken, then in this case, it says that the output of this OR gate, notice that here branch, this is basically my branch control signal, indicates that either we have branch if equal and 0 or branch not equal and not 0. So this is basically my equation. It's actually this logic which is shown here on top. So the branch is taken. So either we have a branch if equal instruction and they are equal, so the branch is taken, or we have branch not equal and they are not equal, so also the branch is also taken in both cases. So that's here is my branch control signal. So if we are branching and we have the jump, okay, this is actually J control signal equal to 1. In order to jump, we have to have that we are not the branching. Okay, because if we are jumping and the branching at the same time, then this jump will be equal to 0. Okay, so this actually JMP will be equal to 0 if we are branching. So this will take care of the situation in which if we have a jump, if we have a branch followed by a jump instruction. So the jump will not take place, the branch will take place. So we'll have here 1, 0. So this will be 1 and this will be 0. And this means that we are going to branch. We are not going to jump. Okay, so this is handled here by this actually here PC control. PC control can detect this situation and it can handle it properly. I just wanted to mention this. Now, kill 1 and kill 2. Yeah. Yes,
okay.
you have a question?
Yes. At the same time, we are jumping, okay, but we don't know if we are branching or not. I mean, the result, it will be at the same time we are jumping. The result of ALU, which is to decide if it's a branch or not.
So now we have the branch is in the third stage of the pipeline, in the execute stage.
Yes.
The ALU is going to produce the 0 flag, while at the same time we have a jump instruction in the second stage of the pipeline. So we have a branch followed by a jump, because the branch has already reached the execute stage, and we have the jump is in the second stage of the pipeline. So the PC control is going to receive J is equal to 1, and say branch is equal to 1. So basically it's going to receive 2 control signals and the 0 flag equal to 1. So it sees that the branch is taken, it sees that there is a jump. After that, it's going to branch, it's not going to jump.
Oh, okay. Okay, it's
Okay.
clear.
So this is why I wrote here, okay, jump here is equal to J and not the branch. Okay. So we will jump only if there is a jump, if there is the J here, okay, it means there is a jump instruction, but we are not really branching. Okay. So there is no branch, okay, which is taken in the third stage. That's what it means. Notice that we have 2 control signals here, kill 1 and kill 2. Okay, the first one is actually jump or branch. So if you are jumping or branching, you kill 1. You kill 2 if you are branching only. Okay, so this will take care of killing, okay, 2 instructions in the pipeline. Kill 1 for jumping, kill 2, kill 1 and kill 2. Both will be used in the case of branching because we kill 2 instructions. There is one slide which is left here, which is about the impact on the CPI. In other words, we would like to see from the performance point of view, okay, how does the jump and the branch impact the CPI? Here's an example about performance. So it says that the base CPI is equal to 1. So we know that in a pipeline, if you have a perfect pipeline, you can complete 1 instruction every cycle. Without taking into account, so assuming that already we have filled the pipeline with instructions, so we can complete 1 instruction every cycle. So that's the base CPI, 1 instruction completed every cycle. Now, this is without counting the jumps and the branches. However, the jump and the branch, as we have seen in my last lecture, is that they have a delay. So it says that assume that the unconditional jumps are 5% of the instructions and the conditional branch are 20%. Now it says that also that 90% of the conditional branches are taken. Okay, and of course the remaining 10% are not taken. The assumption here is that the jump is going to kill the next instruction, which means that it has a delay of 1. That's the meaning of the first part, as we have seen in the simple 5-stage pipeline. And in the case of the branch, it has a delay of 2 cycles. Okay, which means that if you have a branch which is taken, then it will delay it by 2 cycles. All right, so the branch, if it is taken, is going to kill the next 2 instructions because it has a delay of 2 cycles. Remember that the branch is executed in the third stage of the pipeline. And by the time we know the outcome of the branch, already we have fetched the next 2 instructions, and these have to be converted into bubbles, okay, in the pipeline. So it says, what is the effect of the jump and the branch on the CPI? This is the question, okay? So how do we deal with this problem? Any idea? Anyone who would like to volunteer and solve this problem? Students? طيب let me put it this way. Yes, Khalid, تفضل.
Okay. First of all, we have 20% يعني branch.
Right, before the branch, let us call about the jump. Okay, it says that 5% are jump instructions. Now,
Okay, we need to calculate the cycles.
So how do we think about it? How do we think about it? Now, every time we have a jump, the next instruction, if it has a delay of 1, the next instruction has to be converted into a bubble. Okay, according to our pipeline, 5-stage pipeline. Of course, we can do certain things in the architecture to make it much better and to improve the performance, but I will not really go into the details. But according to our 5-stage pipeline, every time we have a jump, we have to convert the next instruction into a bubble, right? So therefore, we lose one cycle. Because the next instruction, yeah, so basically the next instruction is going to go through the pipeline without doing anything. And therefore, we wasted one clock cycle. So rather than going directly to the target instruction, we went into the next one. The next one has been converted into a bubble. So that's a waste of one cycle.
So a jump takes 2 cycles.
In the case of a branch, we waste 2 cycles because we are going to convert the next 2 into bubbles. In the case of a branch. But that's only if the branch is taken. Because we have seen if the branch is not taken, there is no need to convert the next 2 instructions into bubbles. We allow them to proceed and to complete in the pipeline. Right. So if we are going to lose one cycle for every jump, what is the impact on the CPI?
CPI gonna double. Yani we're gonna have 2 CPI for jump instructions.
Yeah, but we only have 5% of the instructions are, only 5% are jumps.
So 0.5 times 2 will give the number of
well, we
cycles.
don't multiply it by 2. Okay, we keep the base CPI, which is 1. We count only the number of wasted cycles. Only count the number of wasted cycles. So we are only losing one cycle. Okay, we are losing one cycle. So basically, we add to the CPI the number of wasted cycles. That's really the idea. Okay, so we add the number of wasted cycles. And in this case, in the case of the jump, we are losing one cycle, but only for 5% of the instructions. So when we multiply 5% by 1, this will give me on average 0.05 cycles per instruction. So if I would like to here to, okay, this is really the idea. So the jump is going to add, notice that we are adding, okay, the wasted cycles. Okay, so without the jumps, without the branches, it is just one cycle per instruction. So every time I have a jump, I have to add one wasted cycle, but only for 5% of the instructions. So therefore, this is one here is the number of wasted cycles here. And the 0.05 are the percent of the instructions which are jumps. So that's the number of wasted cycles. This is what we have to add to the base CPI. Okay. In the case of a branch, how do we handle it in the case of the branch?
90% times 20.
Yeah, times 2. Yeah, we have 20%. Yeah, so we have 20%. Yes. So we have 20% are branches. Okay. And we have, in the case of a branch, 90% of these 20% are taken. So we have to multiply 90% by 20%. And for every taken branch, we are going to waste 2 cycles. So we multiply it by 2 wasted cycles. So that's in the case of the branch. So 2 cycles, 2 wasted cycles multiplied by 20% of the instructions, multiplied by 90% of these 20% that are taken. So this will give me 0.36 cycles per instruction on average. Okay. because we have here 20% of the instructions are branches and 90% are taken. So we get here 0.36, okay, on average, 0.36 wasted cycles per instruction. So now we have wasted 0.05 cycles per instruction, okay, on average for the jumps, and 0.36. So we start with the base, so the new CPI becomes 1 plus the 0.05 plus the 0.36. So we get 1.41. Notice that the 0.41, these are the average number of wasted cycles per instruction. Let me put it differently. Okay, let me put it differently. This is my highlighter here. Now, if I take 100 instructions, how many jumps do you think you have? Okay, so let us take 100 instructions from the program. How many jumps do I have?
5.
5, exactly.
20.
And how many? Yeah, so we have actually 5. Okay, if I have 100 instructions and 5% are jumps, so I have 5 instructions which are jumps. And every time we have a jump which is taken, we have wasted 1 cycle. So we have 5 additional cycles. So if you have 100 instructions and we can complete them at the rate of 100, okay, so one cycle per instruction, so they will take 100 cycles to complete. And if we look at the end of the pipeline, we can complete them at the rate of 1 instruction completed per. Okay, so we can actually finish them 1 per cycle. It takes 1 cycle to finish 1 instruction. Right, so it will take 100 cycles to complete 100 instructions. But because we have jumps, okay, we have 5 jump instructions. These are going to add 5 extra cycles, wasted cycles. So that's actually here the 0.05. That's per instruction. Okay, so you divide the 5 divided by the 100. This will give me the 0.05. Of course, each jump is wasting 1 cycle. In the case of branches, if we have 20% of the instructions are branches and we have 100, so we have 20 branch instructions, right? But we have 90% of these 20 are taken branches. So therefore, we have to multiply the 90% by the 20. This will give me 18 instructions, right? So 90% of 20 will give me 18 instructions will be taken branches. So we have 20, if we have 100 instructions, 20 will be branches, 18 of them will be taken. And every time we have it taken, we are going to waste 2 clock cycles. So therefore, the next 2 instructions are going to be converted into bubbles. So therefore, we get 36 here. But that's actually 36 out of 100. So this is why I'm writing here 0.36. So we are losing. So if we have 100 instructions, we waste 5 cycles for the jumps, and we waste 36 cycles, okay, for the taken branches, for the conditional branches, for those that are taken. So in total, we get 1 plus the 0.05 plus the 0.36. We get the 1.41. That's how we calculate, okay, the new CPI in the presence of, okay, the jumps and the branch instructions. Okay, so that's it. This is actually my example. Yes, Sally, do you have a question?
Yes. Why we start by 1? 1
well,
plus
I'm assuming that it is 1. Okay, because I'm assuming that, okay, if we have no hazards, then you can complete 1 instruction. So it's 1 cycle per instruction. So the instructions are going to complete. We have a large number of instructions, of course, in the program, and I'm ignoring the time to fill the pipeline. So therefore, we are completing 1 instruction every cycle.
Yes,
that's the basic
pipeline.
Yes.